till now, what we were doing was we were um, discussing that how charge particles, which are independent, they will behave in two magnetic fields. Okay. Today, we will take it to another level. Okay. I will tell you the name of the topic later. Now, the diagram is pretty much the same as the one before. So I will take around a minute to make it. So this is I'm now keeping a slice of metal between the two poles of magnet. This is a slice of metal in between two very strong magnets. Hope you understand what I'm trying to show. There is this north pole of a magnet. This is the south pole. And there will be a uniform magnetic field between this north and south pole. And we have a slice of metal in between. This is the width of the metal strip. This is the thickness of the metal strip. So area, cross-section area will be WT. Now listen, pay attention over here. What if we connect it to a circuit where there is current going in from here? This is the current going in. Like, and let's consider current means a positive charge is going in. Now, because of the magnetic field, when a charged particle enters the magnetic field, and we are talking about a moving charge particle, not a charged particle which is at rest, a moving charge particle. When a moving charge particle goes into a magnetic field, it experiences a force. And if you remember this, you can find out the direction the force will be experienced. So I'm making another diagram of the slice. This is the slice. And this is where the positive charge is coming in. And the magnetic field is into the plane of screen right now. And so if you, with your left hand, if you point it towards the screen, your left hand, fingers of your left hand are pointing towards the screen, and your palm is towards right, you can clearly see that when this charge particle comes in, it will experience a force in upward direction. That will make it go like this. But remember, now it is not like this one. There's a difference. In this case, a charged particle was independent. A charged particle was free, and it could move in a perfect circular path. But here, the situation, this is the metal strip. So when there is a metal strip over there, the charged particle which is moving cannot escape. Okay, the charged particle cannot escape out of the strip's body. So what happens is a positive charge accumulates on this side. A positive charge starts to build up on this side, automatically building a negative charge on the other side. So negative charge is built on the other side, positive charge is built on one side. This will produce an electric field. Interesting. Do you think there will be a potential difference between this side and this side?
Yeah.
This potential difference has a name, that is Hall's voltage. What voltage? Hall's voltage. This is today's topic. Hall's
Voltage.
voltage. Now, what happens is when a charged particle goes in through a conductor in a magnetic field, charged particle experiences force, and one side of that conductor becomes positive, the other side becomes negative. And this will produce a potential difference across the sides of the conductor. This potential difference is known as Hall's voltage. When current passes through a conductor that is placed in a magnetic field perpendicularly a potential difference is developed on the sides of the conductor. This potential difference is called Hall's voltage. So this is the definition for Hall's voltage. Now we need to find out the magnitude of this thing. Okay, with the passage of time, when the charge is developing on the up and down, and we know this charge will be exerting a downward force on our upcoming um, charged particles. So there will be a time when the current will start passing through straight. That means that the force because of the electric field and force because of the magnetic field is cancelled out. This is the force because of the electric field, and this is the force because of the magnetic field. Now, force because of the magnetic field equals to B Q V, and force because of electric field will be E Q, and E equals to potential difference divided by distance. Remember, this is Hall's voltage. Listen, if we know this distance, what we can do is we can and okay, let's see how much you understand the diagrams in 2D and 3D. Do you see the question mark I made on the diagram? Can you tell me what will be the size of this thing? If you look at the 3D diagram on the right hand side, can you tell me?
It would be W, the length of W.
Yes, it is W. It is W. W, the length that is shown with W in the 3D diagram is the distance between the sides that will develop the potential. These are the sides that will develop the potential. This and the one side that we cannot see, which is like over there at the back. Okay. So the distance between them will be W. So electric force is delta V over W into Q. And delta V over W into Q equals to B Q V. And we can see that the Q and Q get cancelled. Hall voltage, let's call it Hall voltage, equals to B W V. So there we go. This is one equation to find Hall's voltage. But we know V, which is velocity, equals to drift velocity of charge carriers. So we know the formula for drift velocity, which is V equals to I over area into number density into charge on each particle. So Hall voltage has a new formula now. B W I over A N Q. And this is one formula for finding Hall's voltage. But if you look at this diagram, do you see that this cross-sectional area that we are talking about is W multiplied by T? We did it over here as well. So can I replace area with WT? WI over WT and Q. W got cancelled. All voltage equals to VI over NTQ. And remember, VH is Hall's voltage developed on the sides of the conductor. B is magnetic flux.
Sir.
Then, yep.
Sir, could you excuse me for like 5 minutes? I just need to go break.
Okay.
Okay, thank you.
Current in the metal strip. N is number density. That means number of charged carriers free electrons per unit volume. So number density is number of charge carriers per unit volume. T is thickness of strip. Q is charge on each carrier. So this is a very famous formula that you need for Ohm's voltage. Okay. Now let's solve a question. Okay. Let's solve this question. This is taken from May, June 18, question paper 42. This question number 9. Now, this is the strip I was talking about earlier. Like I made it like this and showed you the magnets on the top and the bottom. Here in this diagram, he did not show the upper and the lower magnets, but he showed these vertical lines passing through the metal strip perpendicularly. Now, this is the magnetic field and the direction the electrons are coming from right. They go in. Electrons enter the slice at a right angle from the face SRXY. The potential difference, the Hall voltage VH, is developed on the two faces of the slice. Use letters from the figure to name the faces between which the Hall voltage is developed. Very good question. Let's see if any one of you can answer. Anyone? What two sides will have this potential difference? Anyone?
PSYW.
Sorry?
PSYW. I mean YV.
Yes, because PSY were in one plane and W was way out of the plane. So that's why I got confused. PSYV. Good, good. And there will like the PSYV is one face.
And then
What will be the
QRW and X.
QRXW. Good. PSYV QRXW. State and explain which of the two faces named is more positive. Now, if electrons are coming this way, electrons are going this way, it means the direction of current is taken to be towards right. Now, with your palm facing okay, if it is electron, you can simply use your right hand palm. Use right hand palm. And we use it for electrons. For current, we use left hand. For electrons, we use right hand. Your fingers should be pointing down. Your fingers should be pointing down. The palm should be towards left. What is your thumb doing? Which side your thumb is pointing at? And use your right hand.
Into the page, or like to
Like
QR
the
XW.
side QRXW or side PSYV.
QRXW.
So that means this side will be turning negative. That means this side has to turn positive. So the question is, state and explain which is more positive. We say PSYV is more positive as electrons experience a force towards QRXW. Okay. Now, use the letters in figure to identify what is T and what is N. Normally, what a student wants to think is T is time. In this case, it is thickness of slice along the magnetic field. Just thickness of slice is okay as well. State the name symbol N. State the meaning of symbol N. Can anybody do that? What is N?
N is like charge velocity or something.
Free electrons per unit volume. State and explain the effect, if any, on the polarity of the Hall voltage when negative charge carriers are replaced with positive charge carriers moving in the same direction. No effect. Positive charged particle experience force in opposite direction. So side PSYV will still be more positive. Listen, he says that instead of using electrons, what if we send protons over here? The protons, like if electrons are experiencing force that way, then proton will experience force in the opposite direction. So that make the side PSYV positive as it is already. So there will be no effect if we replace electrons with protons. Okay?
Yes, sir, makes sense.
Good. So that's it. I think we can end today's class here. And this is also the end of the topic. I will be sending you some questions at the end of the class, and you can give them a try. Okay.
Okay, sir.
Okay. Take care. See you people
All right, sir.
tomorrow.
Assalamu alaikum. Bye.
Officer.
Walaikum salam.